Uh, Hello everyone. This is the NPTEL problem solving session for the course Introduction to Algorithms and Analysis. And intro, this is the problem solving session for week 11. And the primary topics covered in this week in the lectures were disjoint set data structures, union find, the augmented disjoint set data structures, and then primarily network flows. So as usual, we'll uh, try to discuss problems that are related to this week's assignment. And while solving those problems, we'll also go through the theory, right, to make you guys understand the solution a bit better. Okay, so right now I'll start directly with uh, the discussion on disjoint set data structure. And then we'll see some problems on this, right? So the problem of disjoint set data structure, right? It is to maintain a dynamic collection of pairwise disjoint sets, right? Given as S1, S2 to SR, right? Every element of this set S, right? So Si belonging to S has one element distinguished as the representative element, right? And that element has to be unique for every set, and hence it also acts as an identifier for the set, right? And essentially, this is what we mean by these this collection being pairwise disjoint, right? That no two sets have any common elements, right, or any intersection. And this list grows dynamically. So uh, what it does, so we define some operations on the disjoint set structure that we just discussed, right? And it supports, like it has to support three operations, right? And what are those three operations? First one is make set, right? So now X is a new vertex, right? It's just a element, like a singular element. So what this function or this operation does is it adds a new set, right, with a singular value X to S with the representer of the set, the new set, as the original value, right? So that is what the make set does, right? So it is basically to initialize the set, right? Initialize the set that goes inside the collection S, right? So make set, and again, since these are disjoint, so this X cannot be in any of the previous sets for all I, right? So that is the first step, right? To make a new set. Second is the union of two sets X and Y, right? So for X and Y already in S, right? Or let's say for X and Y in distinct sets Sx and Sy, replace these two Sx and Sy with a single set that is the union of the two, right? So whichever two sets contain these elements X and Y, we perform a union of those sets, right? And that forms a new single set inside the collection capital S, right? And the third is find set, right? To find the set containing a certain element, right? And what this function does is it returns the representative element, right? The representative element of the set that contains X, right? Of set S of X containing X, right? So these are the three operations that uh, need to be supported by the disjoint set data structures, right? Like any implementation we do for these kind of data structures, that implementation should have these three operations, right? And what are the different methods of implementing these data structures, right? So we have seen that one is our simple linked list solution, right? And then there is also a simple balanced tree solution, right? Both of these are already discussed in the lectures, and I'm not going to right now expand on these two, give you more details. So we'll take some problems, and while doing those problems, we will see if we need to discuss any of the concepts for these approaches. We'll discuss that. Right? There are some other solutions also that were discussed. Right? First, like there was the augmented linked list solution. Right? So again, I am not going to list all of them here, and also I'm not going to discuss all of them like exhaustively, right? So now I think since you have discussed the disjoint set data structure, let us uh, take a problem, right? So let's take an example. So which of the following operation can return the representative or a pointer to the representative of the set that contains element X, right? So is it find set? Is it make set? Is it merge set? Right? Or is it none of these? So, of course, because we have gone through the definitions of all three operations here, this one becomes straightforward that the only function or the only operation that returns the representative, right? It returns the value of the representative or a pointer to the representative, like depending on the implementation, right? The operation find set, right, gives us the representative, right? So for this, the solution is find set. Okay. Now again, next example in disjoint set data structure. How many operations are there? So is it two? Is it four? Is it three? Or is it five? Right. So again, we saw that in the disjoint set data structure, there are three major or let's three operations, right, that need to be defined: the make set operation, the reunion operation, and the find set operation, right? So again, for this one, there are three operations that are defined. Okay. Let's take another example. What is the depth of any tree if the union operation is performed by height, right? So is it if the union operation is performed by height, then the depth of tree will it be of the order of n? Will it be of the order of log n? Will it be n log n, right? Or will it be something completely different? Okay. So again, since we have been asked about the union operation on a tree, so from here we know that we are talking about the tree-based implementation, right, of the disjoint set data structure. Okay, and it is asking for any tree, but we can analyze for the balanced tree, right, to see what the depth is or what the order of the depth is if the union is performed by height, right? So for this, we'll first discuss the simple balanced tree based solution, right? And from there, we'll see that why is the solution, right, whichever it is. Right? So for simple balanced tree solution, what we do is we store each individual set, right? Si, and where Si is a set of these elements, right? As a balanced tree, ignoring the keys. Right? So every set is a balanced tree, and we define representative element, right? That is the representative of S of I to be the root of the tree, right? So if Si is x1, x2, x3, x4, x5, right? It has 5 elements. Then it will be x1 and then x2, x3, and then x4, x5 become children for x2. Right? So this is the balance tree for this particular set, and this x1 becomes the representative. Right? And how are the three operations defined on this? Right? So for make set, of course, since we are making a new set, we'll need to make a new tree, right? So we initialize x as a lone node, right? And because since it will be the singular node in the entire tree, right? So uh, the operation of creating this set, it's a constant time operation, right? Because we don't need to iterate over anything. We just need to spawn a new node, right? And for find set, right? What we do is we walk up the tree, that contains X until it reaches the representative, right? Because again, for find set, we want to return the representative, right? So until it reaches the root. So this is essentially a walk up the tree, right? So what is the runtime order of a tree walk along its height, right? Because the height is of the order of log n, right? So again, the walk along the height will also be of the same order, right, of log n. And then the union operation, right? Union of x comma y, right? So to perform a union, we concatenate the trees, the two different trees containing x and y, right? So if we have S1 as x1, x2, x3, x4, x5, let's say, and S2 as y1, y2, y3, y4, and y5. We know from the above example how the individual tree for these sets will look like, right? But let's say for this Sx, this xy, we want to perform a union of Sx and Sy. So when we do indeed perform the union, in whatever way we perform union, the like even the worst case, the height of the new tree, right? So the height of the new tree, it will still have the order of log n, right? So again, the union. So for the original question, that what is the order of the depth of the tree, right? Uh, if the union operation is performed by height, right? So it is performed by height. It means that it is the union by rank also, as some sources call it. So whichever has the larger rank, that becomes a new parent, right? But the height is determined by the number of elements, right? The log of the number of elements. So it is the log n, theta of log n uh, algorithm, right? So for our case, this means that the depth of the tree is of the theta log n order, right? For, of course, the tree solution. Right. So let's take the next example. So which algorithm walks left in the list containing x until it reaches the front of the list. And this takes how much? Like what is the order of this in? What is the order of the time taken about by this in worst case? Right. So in this statement, are we talking about the find set algorithm and the it has, in the worst case, a constant uh, time complexity, Or are we talking about make set that has quadratic time complexity? Or are we talking about find set, right? And it has a worst case of linear time complexity? Or we are still talking about find set, but it has n square complexity, right? So again, we saw that in the tree case, the find set was log of n, right? And for make set, it was constant order. But here in this problem, we are told that we are using a list-based approach, right? So if we look at how the simple linked list solution for the disjoint set data structure works, right? So the time complexity for the find set and the unions, like for the operations in a linked list, are different, right? In a linked list based solution are different compared to the balanced tree solution, right? So how we approach the simple linked list solution is we store each set, right, x2 up to x k as an unordered doubly linked list, right? And for that list, we define the first element, the element at front of the list, right? In this case, it will be x1 as the representative element, right? So how does this look? So it's a doubly connected linked list. So we'll have the parent and the like the previous and the next both pointers will have, right? And this first element is the representative element, okay, and the x2, right? So it will have its value here, and this will have its value here, and similarly, right, the last element will also be connected. Okay, so now we also have to define how the operations are defined in this particular implementation, right? So when we are saying we want to make a set, we want to basically start making another doubly linked list, right? So it's basically the initialization, right? So we initialize x as a lone node this time for the list, right? Doubly linked list. But again, since we only have one node, we are only initializing that. It's a constant time operation. Right? And how is find set implemented? We walk left in the list containing x until it reaches the front of the list, right? So it's basically a list traversal. And we know that a list traversal is a linear time algorithm, right? That's one difference that we see here from the balanced tree based solution, right? And how does the union work in this? Right? For union, we concatenate the lists Sx and Sy containing X and Y, right? And the new representative is the representative of X, right? And since we need to concatenate, we need to essentially update all the entries for Sy, right? So again, this union also is a linear time operation. Okay, so in our original problem, right, we wanted to find the operation that walks left in the list containing X until it reaches the front, right? So according to this definition, it is the find set operation, right? And this has like what is the worst case time complexity, right? So it has a theta of n. It takes the order of n time in worst case, right? So that is our option C here. Okay, let's take another example. What is the definition of Ackermann's function? Right, so is it a is I plus 1 for all I greater than equal to 1, or is it a I comma j as I plus j for I greater than equal to j? C is I plus j for only I equal to j. B a 1 comma I as I plus 1, but only for I less than 1. Okay, so for this we simply need to look at the definition of the Ackermann function. Right, so let's look at the definition of the Ackermann function. Right, so for ij, right, it is j plus 1 if I is 0. It is value I minus 1 comma 1 for a positive I and or j as 0 and a of I minus 1 comma a of I comma j minus 1, right? If both I and j are positive, right? And what have we been asked? We are being asked, let's say, so again, if we check this, that then for I equal to j, right? There is no rule that says it will be I plus j, right? Because even for I and j both 0, uh, its value will be 1, right? And not 0 that is indicated by C, right? So C cannot be the case. Uh, Similarly, we can eliminate B, right? And let's try to calculate it for 1 comma I, right? So 1 comma I, uh, it satisfies the, let us say it satisfies the third one, right? So here we have switched I and J. So anyways, we'll try to like stick to it, right? So it is A of 0 comma A of 1 comma I minus 1, right? Assuming that I is also positive. Okay, so now since this evaluation has 0 here, right? So this becomes the first case, right? So this becomes J 1 comma I minus 1 plus 1, right? And we can keep iterating like this, right? But you can see that uh, this value is now just seems like a recursive relation, right? And what we will finally end up with is essentially like for the evaluation of this, we'll have I minus 1 plus 1, right? So because j plus 1, and then we have plus 1 already here, so this value will finally be I plus 1, right? For any value of I, right? For I greater than or equal to 1. Okay, so for this solution will be A, right? Because for any value of I less than 1, right? This becomes negative and the function is not defined for negative value. So I has to be greater than or equal to 1, right? So this less than 1 argument is again wrong, right? And if we assume uh, I as 1, right? When we assume I as 1, this value basically can be calculated like this, right? And then in the next iteration, we'll have a 0 here and I minus 1 here, right? As the same value. So, or we could have just gone this way also, right? Because this will be what a of 0 comma a of what is I here, 1 comma I minus 2, uh, right, plus 1, this one, right? And now since this has 0 here, and this again we'll know that it will keep going, but it will reduce like this, right, for I minus 1. Right? So this value is I minus 1. Right? So we end up with our solution to this. Let's take one more problem. A simple acyclic path between source and sink, which passes through only positive weighted edges, is called what? Right, so is it called the augmenting path, or is it called the critical path, or is it called the residual path, or is it called the maximum path? Right, so again, we just need to have a discussion on the definition here because that's all it is asking, right? So the definition is, right, so augmenting path is basically the path between source and sink that is acyclic. It's a simple path without cycles, right? That is the augmenting path. And what is the critical path? Right, so critical path is the path consisting of zero slack edges, right? And I think residual path was already discussed in the lectures, right? So I think now this is enough for this week's going through this week's assignment and solving it. And whatever problems you might have, you can put them up on the course forum. And I will stop the meeting now. Thank you.